Unit 3. One is thresholding. That is, under Unit 3, mainly we have the topic as segmentation. And basically, by segmentation, we mean that given a particular image, we want to divide this image into parts, and we only want to use the parts which are actually required according to the application. For example, if we have something like a facial recognition system, then the first step basically is to separate out the face from the rest of the image. So we want to separate out the point of interest or the object of interest in our image, and we want to just remove out the background that is present. So in order to do this, we make use of segmentation, wherein we want to describe that these are the pixels that lie as the object in that image, and the rest of this being the background must be removed. So in order to differentiate between pixels belonging to the background and pixels belonging to the object, we have this entire chapter of segmentation. Now, the simplest way in which we can segment an image is by using thresholding. Now, when we say we are thresholding a particular image, it basically means that depending on the pixel values, we are going to decide whether this particular pixel value is beyond the threshold or not. Okay, so if it is greater than the set threshold, then we consider this pixel to be belonging to that particular object. Otherwise, what we have is something called as the band thresholding. That is, if the pixel values belong to a list of pixel intensities which we know are belonging to the object, then we can say that these pixels are the ones which are having so and so intensity, so they will be belonging to the object and not to the background. So an example of basically thresholding is this. So given an original image as this, we can have what we call as thresholding, the simple thresholding. That is, we just have a single threshold, and according to this threshold, we set whichever we say that if the pixel intensity of is greater than this threshold tau, then it has to be set as white or the highest pixel intensity, and if it is below this threshold, then we set it as 0. So what we get after thresholding is most of the times a binary image. So if the pixel intensity is greater than the threshold set, then it will be white in the output image after thresholding. If it is less than the threshold value, then it is going to stay as black. Now, a slight variation to this is called as semi-thresholding, wherein we basically have whichever pixels are having greater than the threshold value, we don't just set it as white, we retain those pixel intensities. Anything less than the threshold, we set those pixels as 0. Okay, that is the only difference between thresholding and semi-thresholding. In thresholding, if the pixel intensity value was greater than the threshold value, that was set as the highest possible one or as 255 or white. Whereas in semi-thresholding, if it is greater than the threshold value, then that pixel's intensity value is retained as it is in the original. We are only changing the intensity, only changing the pixel values of pixels having intensity less than the threshold. We are setting this to 0. So if we can see over here, this part which has certain pixel intensities, that is set as 0. Same thing with the hair. In this upper image, you can see some strands of hair. In this image, all of that has been set to black. Now, this third method is one in which we use band thresholding. That is, if it belongs to a certain pixel levels. Now, normally when we have something like a band pass filter in terms of signal processing, we basically specify that this in frequency that will be passed will be belonging to a certain range. Let's say from x to y, where y is greater than x. So anything in between x to y is considered as passing this filter. The rest is removed. With band thresholding, this is slightly tweaked, wherein we can we may or may not have these values as consecutive values. We can have the passing or the thresholds as a set of pixel intensity values, and if this threshold, if this pixels intensity, gray level intensity value is in belonging to this set of pixels that we have set as the threshold, then only it is set as white. That is the only difference between band thresholding and what we usually consider as band pass filters. Okay, so this may not be consecutive values, but we have a set of values which are considered as the threshold. And if the image's pixel intensity belongs to the set, then we can say that it is set as 1, or the highest pixel intensity. And the rest of the pixel values which are not belonging to the set, they are set as 0. Now, another way in which we can threshold, these three methods are based on the pixel intensity values. Okay, we can do another way, we can segment an image, another way in which we have something called as the histogram based segmentation, in which we first look at the histogram of that particular image. Now, the first method is something called as the mode method, in which we try to find out a histogram which has at least two peaks. That is, if we plot the histogram of this image, we have something like this, wherein I have this particular gray level having the one of the peaks and this gray level having the other peak. Now, the mode based histogram segmentation will work only if we get a valley between these two peaks, that is some dip in this, and secondly we can say that this peak belongs to the background pixels and this peak belongs to the object pixels, or the other way around. At least one of these peaks, we should say, should belong to the object pixels. Then the other peak will be belonging to the background. So this valley that we have over here between these two peaks acts as the threshold. So in mode thresholding, we consider this valley between the two peaks of the threshold as the two peaks, valley between the two values of this peaks as the threshold value, and anything either less than or greater than this threshold will be considered as the object. So we're only setting the pixels belonging to the object depending on this threshold as a object. The rest were as white or 1 or the highest pixel, and the other pixels which will be belonging either to this, let's say that this is my object pixels and this we are assuming as a background pixel. So then all these pixels belonging greater than this threshold value, all of this will be considered as white, and below this threshold will be considered as black. Now, the problem with this approach is that it may or may not give, all the images may not have something like this, a valley between two peaks, the threshold, it's the histogram itself. So what we do is we have something called as the adaptive thresholding or the adaptive threshold segmentation, wherein we divide the entire image into parts, whether it is the size of this image, sub images that we create, that will depend on applications, and we basically divide this entire image into parts, and then we apply histograms to each of these parts, and then to each of these histograms we apply the mode based threshold. Okay, so we'll calculate the histogram of this image, calculate of this individual images, and then we say that these will then come under this valley and peak kind of thing. So we consider this to be the threshold, and anything greater than this threshold will be the object pixels, anything less than this threshold will be the background pixels. And the best method is actually called as the optimal thresholding, or the another name for this is the Otsu's method. Now, since this is actually an iterative method and this basically will require me to write a lot of things, what we'll do is we'll take up this topic on Tuesday's lecture. Okay, I don't have access to the smartboard on Friday, so it becomes a bit difficult to explain. With a mouse, it's just not possible to write all of that. Okay, so what we do in Otsu's method is we just calculate what are the number of pixels belonging to the object and belonging to the this thing background. So based on this, we divide the image into two parts as the background pixel regions approximately, okay, and the object pixel regions. And depending on these two, we calculate what is the average pixel intensity in both these regions. Once we have the average pixel intensities, we consider the threshold to be the average of these two average pixels. So let's say I have region 1 as belonging to the object. I calculate what is going to be the average gray level pixel intensity of this particular region. The same thing I do with the other region, which is belonging to the background. Now, then what I do is I take the average of these two averages. So let's say that my first average was X, that is belonging to the object. The average pixel intensity of the object is X, and the average pixel intensity of the background is Y. So I then take the average as I then take the average of X and Y, and that acts as my threshold. So then what I do is, depending on this new threshold that I calculated, I have to again split this image into based on this threshold as the object and the background regions. Repeat this process of calculating their average pixel intensity, and then calculate their averages, and repeat this process till the difference between the previous threshold and the current threshold is less than a delta value. Okay, so we'll solve I'll give this entire process also because these are formulas, and I'll write all of this in the Tuesday's lecture, and we'll solve numericals also on this. Okay, now, after this, we have edge-based segmentation. Now, in edge-based segmentation, what we do is, given this particular image, we want to divide it and we want to segment this image based on edges. So the most common method is basically what we call as the Canny algorithm or the edge image threshold. Now, in Canny algorithm, what we want to do is we basically prefer using Canny because the gradient operators that we have already studied, those have the problem of producing thick edges. That is, if we use Canny edge detection algorithm, if we use the Privet, Sobel, and Roberts operator, this edges which are white over here, all of those are not going to be a single pixel width. Okay, they are going to be more than that. Secondly, if there is any noise, so if you look at this particular spots over here, these are mainly noise that is there in the image. Now this wall has a bit of black spots, but let's just consider that we want this edge to be just this part without having any spots in between. So that is where the noise also is going to affect your gradient operator. So what we do is we apply Canny edge detection algorithm, in which we try to reduce the effect of noise and also try to get the pixel the width thickness of these edges as small as possible. Okay, so mainly Canny edge detection algorithm is a two-stage process wherein we first apply Gaussian filter to remove any noise present in the image, and second step is to apply gradient processing with something called as the non-maximal suppression. Now this non-maximal suppression is actually thresholding, but instead of using a single threshold, we make use of two thresholds. Now, first, what we would do is basically apply the Gaussian filter to this. So we basically take the convolution of the Gaussian filter with the image, and we would basically, all of these equations are actually written in the textbook. So that is the reason why. So you'll basically be applying Gaussian filter to your image, which will be a convolution operation. Okay, then what we do is, because we want to process the gradients, we have to calculate what are going to be the gradients. Now we had earlier seen that anytime we want to calculate the magnitude of the gradient, we usually use the Manhattan distance or the sum of the components. Okay, but Canny edge detection algorithm specifically requires the calculation of the gradient using the Euclidean distance. Okay, so we basically use this in order to calculate the gradient, and then what we do is we set any pixels are having a particular gradient and its angle depending on whether the left pixel and the right pixel, which of these has the higher gradient value. Depending on that, we set these pixel gradient values as this. That is, if it is greater than the left hand side and whether it is greater than the right hand side. Okay, so we just set this and the angle depending on these conditions. That is, if this angle belongs to in between minus pi by 8 and pi by 8, then we just say that it is from left to right, that is the angle is 0. And P being my central pixel here, I comma j, I just want to find out what is this P1 and P2, because that is going to decide what will be the equations next. Okay, so I'm basically going to consider that if this angle is 0, that is if this gradient angle lies between minus pi by 8 and pi by 8, if you all are having difficulties in understanding what will be pi by 8, this is 0. Pi by 8 I think comes to about 45. I'm not particularly sure. Just check. 360 divided by 8, yeah, 45. Okay, so if it lies between plus and minus 45, we just say that this entire angle is just set as 0 degrees, theta as 0. Okay, that is, we are just discretizing these angles to certain value. And if this angle is 0, then P1 is going to be I and j minus 1, and P2 is going to be I and I plus 1. Pi by, wait, sorry, 36, correct. It comes to, I think, 12, not 360, 180 divided by 8, 22. So not 45, because 45 is also an angle over here. That would be the diagonal, right? Right, thank you, Rahul. So not 45 if this lies between plus 22 and minus 22, then we consider this to be 0 degrees. Okay, somewhere over here it will be. So if it is in this range, then we'll consider this to be set as 0 degrees. And we are basically going from left pixel to the right, the gradient direction. Since we are discretizing that into, instead of having all the possible 180 degrees, we just want it to be either one of this. That is, if it is going from left to right, diagonal topwards, that is diagonal to the up and right, exactly to the up, and somewhat top left to the left, bottom left, down, and bottom right. So if we want angles to be something like this, then we have to discretize all those angles in within this range. Okay, so that is what we are doing over here. So if it lies between 0 and 22.5, we basically set this angle as 0 and say that this pixel is the gradient is going from left to right. Then if it is pi by 8 to 3 pi by 8, something between 23 degrees to let me check, because I also am not familiar with what this values would be. So 22 till 67 degrees. So 23 to 67 degrees. Then it is pi by 4. That is, we set it as 45 degrees. And then we set this that it is actually going in this direction. That is the top right direction. Same thing with this. That is, if we have it in between the other side, then we say that it is in the top left direction. And we are basically going from top left to top right, bottom right, sorry. And if we have the other way around, that is, if it is in the vertical direction, that is in this. So if it lies between 3 pi by 8 and pi by 2, that is 270 and 90. Sorry, not 370. What do we calculate? 67. 67 and 90, if it lies in this range, then we say that it is pi by 2, and we set the pixels p1 and p2 as this. Okay, so after we have this, we basically have something called as thresholding with hysteresis. Now, this is where we use two thresholds, and depending on what our values were of this particular gradient that we calculated here, we basically decide whether to consider this pixel to be belonging to the edge or not. Now, if we basically set two thresholds, the idea is pretty simple. That is, we have two thresholds, a higher one and a smaller one. So we assume that just a minute. Thresholds tau 2 and tau 1, wherein tau 2 is greater than tau 1. Okay, and what we do is we basically say that if the gradient is greater than tau 2, then it will definitely be an edge pixel, and if it is less than tau 1, then it is not an edge pixel. Okay, secondly, if it belongs to this range, that is, if it is greater than tau 1, but it is less than tau 2, then what we do is we basically check the neighborhood pixels of that current pixel, and if that pixel belongs to, if one of those neighboring pixels belongs to any edge that we have already decided, then only we consider this current pixel as an edge pixel. Okay, so in thresholding with hysteresis, we basically do the thresholding with two thresholds, two threshold values, and we are trying to decide whether a particular pixel I comma j can be considered as an edge pixel or not. Okay, so if this gradient value is greater than the higher threshold tau 2, then it is definitely an edge pixel. Okay, if it is less than this lower threshold tau 1, then it is not going to be an edge pixel. Okay, and if it lies between these two thresholds, then we consider it to be an edge pixel only if any of the neighbors of this current pixel have been classified as an edge pixel. Okay, so this is your thresholding with hysteresis. Now, after this, we have something called as edge relaxation. This we'll see in the next lecture. Okay, so if any doubts you'll have, any questions? Okay, then that's it for today. You all can leave the class. Thank you.